So I wanted to talk a bit about performance evaluation for your models. Mostly classification models. Regression is usually pretty straightforward. So in that direction, it's actually important to talk a bit about baseline models. So how do you know if your prediction function is any good? What does good mean? So one version of good is the person who wants the model says, yeah, that's the performance that's above the threshold to be deployable or to be usable. So that's one version. Another is if there's some previous model that attempted to solve the same problem, you compare that, obviously. But if you're kind of, green field, what are some, minimalist baseline models that one should compare to? And it's important to make sure you're doing better than some trivial model. You may start with some very complicated, fancy model. It takes a lot of computational resources. Some neural network running on, $100,000 GPU machine, and you should verify that the thing you're ending up with is better than some trivial prediction function or some simple linear model on 3 features or something like that. So for classification, kind of the simplest baseline to use is called the zero information predictor or the no information prediction function. And basically, it's as simple as looking at your training data, seeing which class label is the most frequent among your class labels, and always predicting that class. All right? So it's called zero information because you literally don't look at the input vector to make your prediction. And so that's something you should always compare to, just to baseline yourself on what kind of prediction accuracy you should be getting. How about for regression? What would the analogous zero information prediction function be for, say, square loss? Say again? The mean of what? The mean of what? Yeah, the mean of the input training vectors, but not the input. The mean of your training outputs. Yeah. Right. Zero information completely ignores the inputs. And how do we know it's the mean? That was a problem on the second homework. So showing that the mean kind of minimizes the expected square loss. OK, so what would it be for absolute loss? Have to ask. So instead of square loss, we have absolute loss. Median. That's the median, right? Median on the training data. Median of the responses on the training data. OK, good. So got the zero information baselines out of the way. Next, try using one feature at a time. OK? Try building a simple model, maybe a linear model, or we'll do decision stumps later that use just one feature at a time. Find the one that works the best and let that be your next simplest baseline. Okay. Everything we've talked about so far could probably be considered a baseline for future exploration. So if you don't invest too much in feature engineering, implementing a regularized linear model, right? So that's regularized ridge regression or SVM or regularized logistic regression. These are linear models that are generally fast and easy to understand, and invest some time into those baseline models, probably before or concurrently with doing something fancier if you can. So, and spend a little bit of time on feature engineering, just to make sure you understand roughly what's happening and what's helping. So, and it's a good baseline. So if it'll often happen that your fancier model, your gradient boosting or your neural network or your random forest doesn't beat your linear method out of the box. So often that tells you that you're not training your fancy method quite right. Maybe you need to change some hyperparameters or something. Maybe you just don't have enough data, or maybe it's just not the right fit. Maybe a linear model is actually the right fit in the particular setting. But but not beating your baseline models, that's a warning sign that something's not quite right. And when you have these very complicated models, it's good to have some signposts, like I should be able to at least do this well because I have a simpler model that does that well. All right. At the other extreme is what you can call an oracle model, which is a model that's not a legit model because you intentionally cheat in building this oracle model. So, but the idea is to get some kind of an upper bound on the performance that you can potentially achieve. You know, if your accuracy is 64%, and they're like, it's terrible, 64%, people get like 95% on classification tasks. And then you could find an oracle model that kind of demonstrates that you can't possibly beat 70%. That puts the 64% in a much more favorable light. So what could this look like? So you basically allow yourself to look at the validation or test set in building your model. So if you were to look at your validation set and you were given free rein to build any prediction function you want, is there any reason you wouldn't be able to achieve zero loss? Yeah?
If you have different outputs for the same input.
Great. So that's our go-to counterexample. If you have two inputs with different outputs, you will never be able to achieve zero loss because a prediction function is a deterministic function. For any input, it has to give a particular output. So you're either going to get one or you're going to get the other, but you cannot get both. Great. So already we see that an oracle model is not always going to be perfect. So what we're going for here, though, is an estimate of the Bayes risk. In other words, the optimal error rate achievable with any prediction function. So if you go crazy fitting your validation data, then you're kind of getting towards an estimate of the Bayes risk if you allow yourself any type of prediction function. All right. A more restricted kind of oracle model would be restrict yourself to the class of functions you're using. Like maybe you're considering linear regression with a certain set of features. Well, if you take that same linear regression, you get rid of regularization, you fit your validation data with that model, the performance you get with that fit, that kind of gives you like the best possible performance you can hope to achieve on that with that validation set. So in some sense, that's kind of getting at the approximation error of your hypothesis space. So in other words, if you had infinite training data, even if you had infinite training data, you're not going to be able to do as well as the model that fits directly on the validation data. Is that clear? So, and the gap there, the reason that you, if your fit to the validation data doesn't do as well as you'd like, that means that the hypothesis space that you're pulling that prediction function from isn't rich enough. It just can't fit the validation data as well as you would like. So that would be a clue that you need to either get a more, you need to enrich your hypothesis space either by making more features or by using some fancier model that is more expressive. So oracles are good to compute, to give you some baseline and an oracle, and then you know you're somewhere in between is the achievable range. Okay. All right. So you've got your baselines, fine. What metrics are we actually going to use to evaluate the performance of a classifier? What have we talked about so far? In the homework, I think we only have accuracy and error rate. Is that right? So let's introduce a few concepts here. First is a confusion matrix. Confusion matrix is a simple summary of the results of a binary classification. We'll name the two classes 0 and 1, and there's kind of 4 possibilities. For any given example, the real class can be 0, and you can predict 0. And confusion matrix counts how many outcomes of each occurred. So the A here says that A times in your validation set, the actual class of an example is 0 and you predicted 0. B times the actual class was 1 and you predicted 0. That's an error, etc. Right? So these four numbers, A, B, C, D, summarize pretty much what everyone tries to get out of the result of a classification. And a lot of the remaining slides are how do you go from 4 numbers to 1 or 2? Because you can only optimize on one. You can only choose a model that does the best on a single number, on a single ranking. So different ways of combining A, B, C, and D give you kind of different scores. Okay. So accuracy is the first. Accuracy, of course, is going to be the ratio of the correct count to the total count. Error rate would be 1 minus the accuracy. For most every other, oh, sorry, I got ahead of myself. So besides accuracy, you can also talk about accuracy on different subgroups. And the natural subgroups of your examples are going to be kind of the subgroup of examples that are of class 0, the subgroup of examples that are of class 1, and the subgroup of examples that you predicted class 0, and a subgroup of examples you predicted class 1. And so those would give you 4 different measures of accuracy on 4 different, not disjoint, but 4 different subgroups of your data. And these will come up with different names later on. So just a quick example on why accuracy is not really sufficient. So here is, we created a no information classifier. And here's our confusion matrix. And what's going on here is that we have 10,000 class 0s and 9 class 1s. And we're just always predicting class 0, because that's the dominant class. So the accuracy is great, 99.9%. Error rate's quite small. But this is not, accuracy doesn't really capture what's going on here. So for instance, it's not capturing the fact that you have a 100% error rate on class 1. And that might be relevant to how you assess the performance. And the other thing is, of course, this kind of makes very clear that you need to have in mind what your no information rate is if you want to evaluate a candidate for improving on this performance. All right. So for most of the metrics we're going to talk about, there's kind of a favored class called the positive class. But until now, we've never had any particular, we've treated classes symmetric. We called them -1 and 1, we've called them 0, 1, we've called them A and B. It doesn't matter, they're symmetric. But now, conceptually, we're gonna try to differentiate them. So in many contexts, it's kind of natural to define a positive class and a negative class. So we'll just go through some examples to build your intuition here. So you take a medical test, like a pregnancy test. Positive, you're pregnant. Negative, you're not. It's like a medical diagnostic thing. A radar system. Positive, there's a threat detected. Negative, nothing unusual going on. Right? You're searching for documents in Bitcoin. It's Google, or it's a library catalog. Positive is, this document is about Bitcoin. Negative is, it's like most documents and not about Bitcoin. Right? Statistical hypothesis testing you could put into this framework. Positive is you reject the null hypothesis. That's supposed to be kind of the more rare event. All right, so it's just loosely speaking, positive is maybe it's less frequently occurring. Maybe it's the more significant outcome, something to get excited about. Anyway, and depending on exactly how we think positive is different from negative will determine the metrics that we're interested in as a summary of performance. So here's our way to write the confusion matrix for positive and negatives. There's this notion of true positive. A true positive would be the actual class is positive and we predicted positive. I find these hard to remember. A false negative would be you said it's negative, but that's false. It's wrong. And the actual class is positive. So we have false positive and true negative and true positive and false negative. And I guess when you say positive or negative, that's about what you predicted. And the true or false is whether it's correct or not. That's how you put it together. So false positive is, I predicted positive, but that's false. It's not positive. So the true class is negative. All right. OK. So the first terms we're going to introduce are precision and recall. Have you guys heard precision and recall? Yeah, it goes around a lot. There's a lot of terms. I think we're going to talk about like 8 terms. And to remember what's what, it helps me a lot to think of the context that uses these terms. So precision and recall is used a lot in information retrieval. It's like when you're querying a database or doing a search or something. So the precision is the accuracy of the positive predictions. So if you have a database you're querying, you query for Bitcoin. The search engine or database returns a whole bunch of documents and it says, I think all these are about Bitcoin. It gives you a whole bunch. The precision is the accuracy of the things it gave you as far as pertaining to your search term. So it's the fraction of the things that the search engine returned that are actually pertaining to what you search for. All right? So if precision is high, most of the things it gives you are relevant. If precision is low, you're sifting through a bunch of irrelevant stuff to find the relevant stuff. That's precision. Recall is kind of the counterpart. Recall is how many of those documents in that database that are relevant did you actually find for me? So if recall is really high, you pretty much scoured everything and there's nothing missing from the document set you returned to me. If recall is low, it means even if everything you gave me was relevant, there may be a lot more relevant you didn't find for me. All right. So in some sense, you want high precision and high recall, ideally. But in reality, one has to trade off between these things. Because how could one get perfect recall?
Return everything you got.
Yeah, if you just return everything, you have perfect recall, trivially, but also not usefully. I don't think there's a trick to get perfect precision.
Return nothing.
What? Return nothing would kind of give you a divide by, oh yeah, that'd be 0 over, yeah, OK. No, that'd be 0 over 0, wouldn't it? So I think precision is not defined if you return nothing. OK, but yeah, if you only return the one thing you're most confident in, then OK, the precision will be high. So if you have some kind of a confidence score, you should be able to get precision higher by returning the things you're most confident about. OK. All right, so yeah, let's do this quick example. All right, so we have 100,000 documents. We query for Bitcoin. We get 200 documents back. 100 of them are actually about Bitcoin. 50 documents weren't returned to us. We can populate this confusion matrix table. So what's the precision? First of all, our query returned 200 documents. So what's the precision of this result?
50%.
50%? How do you get that?
We look at what we predicted to be true, so 100 plus 100 is 200.
All right, so the predicted positive class is this row, 100 and 100, OK.
And then 100 were actually right.
100 were actually positive and 100 were negative, so 50% precision. OK, great. And what's the recall here? 2/3, because the recall is about how of the documents that actually are relevant, of which there are 150, how many were returned to you? 100. So 100 out of 150, so 2/3. Good. All right, so precision and recall. Great. All right. There's this thing called F1 score. So the issue is that you kind of want precision and recall to be both good. You need a way to combine them to get a single number if you want to rank a set of prediction functions or score functions. So there's this notion of F1 score. It's just one of many, infinitely many possible ways to combine precision and recall. But this one is used very commonly. So it has this formula. So the F1 score is the harmonic mean of precision and recall. which has this formula, but I've plotted the harmonic mean as a function of precision and recall for you. And if you look at the formula, you could see pretty easily that if precision is equal to recall, then the harmonic mean is whatever precision and recall are, if they're equal. If either precision or recall is 0, the harmonic mean is 0. So that's what the edges of these graphs are. So this surface is the harmonic mean of the kind of x-axis and y-axis. You see it goes to 0 at the edges. And kind of the x equals y line, or precision equals recall line, the harmonic mean is itself precision and recall. And then it kind of interpolates smoothly in between. So I made a little table here to get some sense of how F1 combines precision and recall. If precision is really small and recall is really large, the F1 score, the harmonic mean, is really small. So it's almost like the minimum of these things, but not quite. So 0.2 and 0.8 averages to 0.32. It's much closer to the smaller, 0.4 and 0.9, 0.55. When they're almost equal, F1 score is almost equal. And when they're both large, it's somewhere in between, but it also favors the smaller one. All right, so that's F1. You see it all the time. It balances. You'll notice it's symmetric between precision and recall, but you may want to prefer one or the other. And then there's this thing, it's much less used, but F beta. And this gives you a way to weigh precision or recall more or less heavily. So here's F1/2 and F2. And you could look at you could see that it interpolates more towards one or more towards the other. All right. So in one domain, precision, recall, and F1 is a very common scoring system. In other domains, notions of true positive rate, false positive rate, true negative, and false negative are used a lot. So again, this is hard for me to remember, but true positive rate is the accuracy of the positive class, the true positives. So it's how accurate were you on that subset of examples, which is exactly recall. All right. False negative rate, again, so this is confusing, right? This is the error rate on the positive class. So this is the true positive rate is the accuracy in the positive class. False negative rate is the error on the positive class. So one is 1 minus the other one. Anyway, false positive rate, that's like a false alarm. If the positive is kind of a bad thing, like incoming missile, then a false alarm that'd be the false positive. Okay. And I kind of put this here as a reference. You could just quickly remind yourself what all these things are. So another set of terms that show up a lot, medical diagnostic setting would be one place, is sensitivity and specificity. Right? There's just another way to put these true positives and false positives together. So sensitivity is another term for true positive rate, which is also a term for recall. So that we've seen before. And in the medical context, it's like of the people who have the disease, what fraction do we find? So you want that to be high for a medical diagnostic test. You don't want to miss a disease that someone has. That would be very bad. So you want sensitivity to be high so you don't miss anything. And the alternative is, the other side of that is specificity. So this is what fraction of people without the disease do we identify as not having the disease. So this is about false alarms. So someone gets a test, and if specificity is 90%, that means that 90% of people who don't have the disease will be told you did not test positive, which is good. So the flip side is false alarm. All right. So of course you kind of want them both to be high. Statistical hypothesis testing you can kind of put in this framework as well. So there's kind of one decision to make in a hypothesis test. Do you reject the null hypothesis, or do you not reject the null hypothesis? So you want to reject the null hypothesis. That's like predicting a positive. That's the unusual event. and negative would be don't reject. So in our table, if you shouldn't reject the null hypothesis is correct, but you predict positive, so that's like rejecting it. It's called a type 1 error. And if you do have an anomaly, so you do want to reject the null hypothesis, but you don't, that's called a type 2 error. So that's how our statistics terminology fits in here. All right. Any questions? All right, just a little bit more here. So when we developed classification, we very quickly jumped to a setting where we had these real value prediction functions called score functions. And the default was if the score function is greater than 0, it's like predicting 1. And if it's less than 0, it's like predicting -1. So 0 as a threshold was reasonable, and we worked with that when we developed things. But we don't have to use that threshold. We can change that threshold. So here's an example of, here's a bunch of score functions produced by some prediction score function. I've sorted them from lowest to highest. And thresholding at 0, so anything above the line is negative, anything below the line is positive. So thresholding at 0 would make everything above the line be a negative prediction and below a positive prediction. And then over here we have the true class labels for negative and positive. So how many errors, what's the error rate here? 4 out of 12, 1/3, great. And what's the precision? So precision is, you look at the things that were predicted as positive, and then what's the accuracy on that subset? 4 out of 6, great. So the precision is 4 out of 6. And what's the recall here? Recall is of all the positives, of all the true positives, 1, 2, 3, 4, 5, 6, how many did you find? And that would be 4 of them, 4 out of 6, great. Okay. And the F1? 4 out of 6, that's right. Okay. Now let's go crazy and change a threshold. So this was a threshold of 0. What if we move the threshold down here between 8 and 9, say a threshold of 2? And we only predict positive if you're greater than 2 and otherwise negative. So what happens to our error rate if our threshold, if these two are negative and only predict these bottom 4 positive? What's our error rate? I count 2 errors. If these were negative, these were the only errors, 2 out of 12. Precision, only these 4 are predicted positive, and they're all correct, so that's 100%. And recall, so the positive classes stay the same. We're missing 2 still. So 4 out of 6, great. All right, so by changing the threshold, we got a whole different set of performance metrics. We could change the score to -1 and another new set. So what threshold should you choose? I mean, the fact that 0 is somehow natural for the formulation is irrelevant. We should choose a threshold that gives us the performance metrics that we're most interested in. So we need to figure out, do we want to optimize F1? Do we want to optimize for precision, for recall? I mean, if you have a business objective you can write down precisely, you should always try to do that. One common form of optimization would be set a minimum requirement for, say, recall. Like, I don't want to miss more than 20% of the documents that I should be getting back. But as long as I have 80% of the documents that are relevant, I want to get rid of as much junk as possible. So I want to maximize the precision subject to a constraint that my recall is 80%. That would be another form of a metric you can look at. All right. So we've talked about performance metrics for a single prediction function, a single score function with a threshold. We've talked about changing your threshold to get different performance metrics. And then I want to introduce you briefly to these curves that show up all the time. And I guess the idea is that as you vary your threshold, you get a whole sequence of performance metrics. And you can plot those performance metrics, and that gives you various curves. So this, for instance, is a precision recall curve. So as you vary the threshold, not on this data, but on some other data, you get different trade-offs between precision on the y-axis and recall on the x-axis. You can do a little bit of reasoning and see that if you start your threshold really large and you gradually decrease it, you'll see that recall keeps increasing. Why? Because as you move your threshold up, you're gradually predicting more and more positive classes. So of course your recall, how many true positives you found, would only be increasing. Precision can go up and down as you change your threshold. And that's why you get this weird kind of bounciness, because although as you change your threshold, your recall marches steadily higher, your precision can go up and down. But generally speaking, as you decrease your threshold, would you expect precision to go up or down in some kind of an average sense? So you start here and you decrease your threshold. Suppose we really move into the intuition that the score represents our confidence. So we'd expect something with a very high confidence to be more likely to be a true positive. So we'd expect the precision for the first few things that we're predicting positive to maybe be higher than the precision as we get lower down in the list. Okay. All right. There's also something called an ROC curve, which you'll hear about quite a lot. And that doesn't have the bounciness. It just steadily, it monotonically increases. The true positive rate is on the y-axis. The false positive rate is on the x-axis. And the ideal would be low false positive, high true positive. So we want performances that are in this corner. In the precision recall, we want performances that are high recall and high precision, so in this corner. So in this graph, in this plot, if you're OK with precision around, I don't know, 83%, you can achieve it here, but as you move more to the right, you're getting much better recall for about the same precision. So you'd probably want to choose something like here, the model, the threshold that gave you this performance. Okay. So these curves give you some sense of the frontier of metrics that are achievable by tuning your threshold. So every single point here is a trade-off between true positive and false positive that you can achieve by adjusting your threshold. And you have to decide what you want. Here's 3 prediction functions with the ROC curve. And you can plot them all together. And what you'll see is that no one function dominates the others. But at different fixed false positive rates, one of these curves will be better than the other. So if you wanted a false positive rate of 0.2, the one that has the best true positive rate at that point might be this black curve, corresponding to a particular prediction function with particular threshold. All right. But if you don't have a specific trade-off you have in mind a priori, and you just kind of want to compare the performance of various methods, there's ways to summarize these whole curves into single numbers. And the standard way, the most vanilla way to do that is to look at the area under these curves. So that's called AUC, RUC, area under the curve, ROC. Or often, if it's for the ROC curve, it's usually just, when people write AUC, they really mean the area under the ROC curve, typically. And that's a way to summarize with a single number the performance of a classifier without having to figure out your threshold. Yeah, you can also do the area under the first part of the curve. Maybe this is the area that's most interesting to you, and so you might look at kind of just the area on the first fraction. Various tweaks you can do. There's really a lot more one can say about AUC, but I don't think we need to go into it right now. The last thing I wanted to show you is something that's very useful in business. This returns to the churn problem we talked about in the first lecture. So remember in the churn problem, the idea was that there's these people who might be changing phone carriers, and the action you could take is to give them some incentive, some promotion to get them to stay. The promotion costs you money, but the hope is that it costs you less than the money you lose if they leave and go to another company. So you can have this machine learning problem where you look at some historical data and you figure out how to predict the likelihood that each person is going to churn. And you kind of rank them by how likely they are to churn. And then the question is, which of these people should you give the promotion to? How many of them? The idea would be you start at the top of the list with the most likely to churn, and you go down and you stop at a certain point. And so you get these lift curves are a very natural way to evaluate that sort of situation. So the x-axis is, you imagine you have a ranked list of all your users. The highest on the list are the most likely to churn according to your model, and it decreases as you go. And as you move from left to right on this x-axis, this is how many people off the top of your list are you going to target with the promotion. So here, at this point, 50,000. I'm going to look at 50,000 out of 250,000 and give them all a promotion. And if you gave that top-ranked 50,000 the promotion, what fraction or how many of those people will actually be churners? And that's what these curves tell you, called cumulative successes. How many of your predictions for churn were correct if you look at the top 50,000 of your list, the top 100,000, the top 150,000. And what you want to see usually is that you want to see the curve increasing as quickly as possible. You want the top of the list to be the most accurate. And then depending on how many users you're willing to target, maybe you only have a budget for 50,000, you choose the model that gives the highest predicted cumulative successes for that number of trials, that number of users. All right. This diagonal line is baseline, where you give everyone a random score. And similar to ROC, you can see that's just going to go a straight line from the bottom left to the maximum top right. All right, that's all we have to say for today on this performance evaluation. You got a question?
Could you imagine like a similar mental model for like doing anomaly detection or something? Like maybe out of a lot of data points, like some of those could be bad, and then you have like some notion of time, which might be like the money spent for promotion, time to investigate whether they're correct or not. So you similarly want to like sort your list of data points in decreasing order of the likelihood of being bad, and then allocate time accordingly.
Yeah, anomaly detection would fit this fairly well. If it's a little less natural, which is there may not be a hard threshold for how many anomalies you'd want to investigate. Maybe your team has a certain capacity for how many anomalies to investigate, and then that would be your number of investigations. Right. You could also do like a profit curve, where you take it one step further and you include, instead of successes, you have kind of net profit, which would be, you'd account for how much money you have to spend to give the promotion of this many users, and then given this is the fraction of people who you recruited, how much money did you save, and then you'll get a different curve that would be your expected payoff, and then you could maximize that if you had more information on what you're after.